the evening is quiet, and the pace of the day has begun to slow. In the next while, we will move gently through the long history of food preservation, tracing how people learned to keep food safe and edible across days, seasons, and journeys. If you enjoy calm explorations like this, you may consider subscribing to the channel for more slow and thoughtful stories. Human life has always been closely tied to food, and food has always been tied to time. Fresh plants and freshly caught animals begin to change almost immediately after harvest or death. Microorganisms grow. Enzymes continue their work inside tissues, and the chemistry of living matter gradually shifts. Without some form of preservation, many foods remain edible for only a short while. Because of this, the story of civilization is also a story of learning how to slow these natural processes. Long before written history, early human communities were already observing how food behaved over time. In warm climates, meat left in the open could spoil within hours. In cooler air, the same meat might last longer. A fish placed near a smoky fire could remain edible longer than one left exposed to insects. These observations accumulated slowly, through daily experience rather than formal science. The earliest methods of preservation were simple extensions of the environment. Cold air, dry wind, sunlight, and smoke all became quiet partners in keeping food usable. Early humans did not describe these processes in terms of bacteria or enzymes. Those explanations would come much later. Instead, preservation was understood through practice. If something worked, it was repeated. Drying is among the oldest known preservation methods. Water is essential for most microbial growth. When food is dried, the available moisture decreases, making it harder for bacteria and molds to multiply. In many parts of the ancient world, sunlight and wind provided a natural drying system. Thin strips of meat, fish, or plant foods could be placed on rocks, branches, or woven mats. Archaeological evidence suggests that drying meat was practiced tens of thousands of years ago. Hunters who brought down large animals faced a practical problem. A single animal often provided more meat than a small group could eat in 1 or 2 days. Drying offered a solution. Meat could be sliced thin and exposed to sun and air, gradually losing moisture until it became firm and lightweight. The dried meat could then be stored for later use. In colder climates, it might be kept in skin bags or hung in sheltered areas. In warmer regions, it might be protected from insects using smoke or ash. Though the details varied by culture and climate, the principle remained consistent. Less water meant slower decay. Plant foods were also preserved through drying. Wild berries, nuts, roots, and grains could all benefit from the removal of moisture. Some early agricultural societies learned to dry harvested grains before storage. When grains are harvested with too much moisture, they can develop mold during storage. Drying them in the sun reduced this risk. Even today, drying remains one of the simplest and most widespread preservation methods. The underlying biological principle is now well understood. Microorganisms require available water for metabolic activity. By reducing water activity, drying slows or stops their growth. Early humans did not describe the process in these terms. Yet their practices aligned closely with what modern microbiology would later confirm. Another ancient preservation method developed alongside drying, and that method was smoking. Smoke is produced when organic material, such as wood, burns slowly, releasing a mixture of gases and tiny particles. Some of these compounds have antimicrobial properties. Others help protect food by creating a physical barrier on its surface. When meat or fish is hung above a slow fire, the heat gently dries the surface, while smoke deposits chemical compounds onto the tissue. Over time, the food becomes both drier and chemically altered in ways that discourage bacterial growth. Smoking also changes the flavor, producing the distinctive aromas associated with smoked foods. Archaeologists have found evidence of ancient hearths and smokehouses in many early human settlements. In colder northern regions, smoking became particularly important for preserving fish. Rivers and coastal waters often provided seasonal abundance. During periods of heavy fishing, communities could catch far more fish than they could eat immediately. By smoking the surplus fish, they created stores that could last for weeks or months. These preserved foods helped bridge the gap between seasons of plenty and seasons of scarcity. In this quiet way, preservation practices supported the stability of early societies. Salt preservation emerged somewhat later, but would become one of the most influential techniques in food history. Salt occurs naturally in many parts of the world, often in coastal areas or mineral deposits. Ancient people noticed that foods treated with salt behaved differently over time. Salted meat or fish could remain edible much longer than untreated food. The reason lies in osmotic pressure. Salt draws water out of microbial cells and also removes moisture from the food itself. With less available water, many microorganisms struggle to survive or reproduce. The surface of salted food becomes an environment that is difficult for many bacteria to inhabit. Salt could be applied in several ways. Food might be packed in dry salt, rubbed with salt crystals, or soaked in concentrated brine solutions. In some traditions, salt preservation was combined with drying or smoking to produce even greater stability. As communities became more organized and trade networks expanded, salt gained economic importance. Some ancient societies built entire trade routes around the movement of salt. Roman soldiers were sometimes partly compensated with salt allowances, which is one possible origin of the word salary. Salted foods played a central role in long-distance travel. Armies, merchants, and explorers needed food that could survive weeks or months of transport. Salted fish, salted pork, and preserved meats became essential components of these journeys. The relationship between preservation and mobility was becoming clearer. While drying, smoking, and salting relied largely on removing moisture or altering the surface environment. Another method of preservation developed through a different mechanism. This method was fermentation. Fermentation occurs when certain microorganisms transform sugars and other nutrients into new chemical compounds. These transformations often produce acids, alcohols, or other substances that inhibit the growth of harmful microbes. In effect, fermentation allows beneficial microorganisms to create conditions that limit competitors. The discovery of fermentation likely began with observation rather than intention. Fruits left in containers might develop alcoholic liquids. Grains soaked in water might begin to bubble and change aroma. Milk stored in warm environments might thicken and develop a sour taste. Over time, early communities learned that some of these transformations produced foods that lasted longer than their fresh counterparts. Fermented milk products such as yogurt and kefir could remain edible longer than fresh milk. Fermented vegetables developed acidic environments that discouraged spoilage organisms. One of the earliest known fermented foods is probably fermented grain beverages. Evidence from archaeological sites suggests that people in ancient China were fermenting rice, honey, and fruit mixtures more than 8,000 years ago. Similar developments occurred independently in other parts of the world. Fermentation did not only preserve food, it also transformed flavors, textures, and nutritional properties. In many cases, fermentation increased digestibility or introduced beneficial microbial cultures into the diet. The connection between fermentation and microbial health would not be scientifically described until much later, but traditional cultures recognized the practical benefits. Vegetable fermentation became especially important in agricultural societies. When large harvests arrived at once, preservation became necessary. Cabbage, cucumbers, and other vegetables could be packed in salt brine and allowed to ferment naturally. Lactic acid bacteria gradually converted sugars into lactic acid, lowering the pH of the environment. The resulting acidic conditions prevented many harmful microorganisms from growing. Foods such as sauerkraut, kimchi, and pickles developed through variations of this process. Though the ingredients and spices differed across regions, the underlying microbial transformation was similar. In colder climates, fermentation provided an effective way to store vegetables through the winter months. Underground storage pits or cool cellars helped maintain stable temperatures, while fermentation slowly progressed. These preserved vegetables offered both nutrition and variety during seasons when fresh produce was unavailable. Meanwhile, in pastoral societies where milk was abundant, fermentation produced an entire family of preserved dairy foods. Yogurt, cheese, kefir, and other fermented milk products emerged through the combined actions of bacteria and sometimes molds. The acid produced during fermentation helped stabilize the food, while salt and drying sometimes added further protection. Cheese in particular represents a complex form of preservation. When milk is curdled using enzymes or acids, the solid curds separate from liquid whey. The curds can then be pressed, salted, and aged. During aging, microbial activity continues in controlled ways, shaping flavor and texture while limiting the growth of harmful organisms. Some cheeses are aged only briefly. Others mature for months or years. The process reflects a deep cultural knowledge built over centuries of observation. Long before microbiology, cheesemakers were managing microbial ecosystems through temperature, humidity, salt, and time. As human societies grew more complex, preservation techniques became increasingly systematic. Storage structures appeared in many regions. Granaries were built to keep grains dry and protected from pests. Clay jars sealed with wax or resin helped store oils, grains, and preserved foods. In ancient Egypt, food preservation was closely connected to climate. The dry desert air naturally supported drying processes. Fish and meats could be salted and dried, while grains were stored in large communal facilities. These practices helped sustain large populations along the Nile. Egyptian tomb paintings and archaeological finds reveal scenes of fish being cleaned, salted, and laid out to dry. Such imagery suggests that preservation was not only practical, but also deeply integrated into daily life. Similar practices appeared across the Mediterranean world. In ancient Greece and Rome, salted fish sauces, such as garum, became widely consumed. Garum was produced by fermenting fish parts with salt in large containers exposed to sun and heat. Over time, the mixture broke down into a liquid rich in amino acids and strong flavors. Though the aroma could be intense, garum was valued as a seasoning and preservation product. Its production involved controlled fermentation under salty conditions that limited harmful microbial growth. Large garum production facilities existed along Mediterranean coasts, indicating a developed industry. Throughout these early developments, preservation remained closely tied to local environments. Methods evolved according to climate, available resources, and cultural traditions. Northern communities relied more heavily on smoking and drying. Warmer regions used fermentation and salting in combination with sunlight. Across continents and centuries, people continued refining these techniques through quiet experimentation. No single invention created food preservation. Instead, it emerged gradually, shaped by countless small observations made during cooking, farming, hunting, and storage. As the centuries passed and trade expanded, preserved foods began to travel far from their places of origin. Salted fish from coastal areas reached inland markets. Dried fruits moved along caravan routes. Fermented products crossed cultural boundaries, sometimes adapting to new ingredients and tastes. The spread of preserved foods allowed societies to support larger populations and more complex economies. Cities could grow because food from distant regions could be transported and stored. Armies could move because preserved supplies traveled with them. Seasonal harvests could be stretched across the entire year. Yet despite these advances, preservation remained limited by natural conditions. Without modern refrigeration or sealed containers, many foods still faced relatively short storage lives. Spoilage remained common, and communities continued searching for better ways to control the passage of time in food. Over many centuries, gradual improvements accumulated. Techniques became more refined. Storage structures became more sophisticated. Knowledge passed from generation to generation through daily practice rather than written manuals. Eventually, the growth of global exploration, scientific curiosity, and industrial development would transform food preservation in ways earlier societies could not have imagined. But before those changes arrived, the foundations had already been laid through thousands of years of careful observation. The early history of food preservation is therefore not a story of sudden breakthroughs. It is a long, steady process of learning how the natural world behaves. People watched how food changed, and they adjusted their methods accordingly. Dry air slowed decay. Salt reshaped microbial environments. Smoke introduced protective compounds. Fermentation harnessed microscopic life to create stability. Each method reflected a partnership between human intention and natural processes. As we continue forward through this quiet history, we will gradually see how these ancient techniques evolved, how they supported expanding civilizations, and how scientific understanding slowly revealed the invisible biological forces that had always been present within preserved food. As centuries passed, preservation practices settled quietly into the routines of daily life. Most people did not think of them as special techniques. They were simply part of preparing food for the future. In farming communities, the rhythm of preservation followed the rhythm of harvests. When crops matured all at once, people worked steadily to store what could not be eaten immediately. Grain storage was one of the most important forms of early preservation. Unlike fresh fruits or meat, properly dried grain can remain stable for long periods of time. Wheat, barley, rice, and other cereals contain relatively little moisture when harvested and dried correctly. This natural dryness slows microbial activity and reduces spoilage. Ancient societies devoted careful attention to storing these grains. Archaeological sites from Mesopotamia, Egypt, China, and the Indus Valley all reveal large storage structures designed for this purpose. Some were simple clay bins. Others were large communal granaries, built with thick walls and raised floors to keep grain dry and protected from pests. The design of these structures was not accidental. Builders understood that air movement, dryness, and separation from ground moisture were essential. Floors were sometimes raised on stone or wooden supports. Walls were thick enough to reduce temperature fluctuations. Small openings allowed ventilation, while limiting access for rodents and insects. Grain preservation supported the development of early cities. When harvests could be stored safely, food supplies became more predictable. Communities could survive seasons when fresh crops were unavailable. Stored grain also allowed governments and temples to collect taxes in the form of food, which could later be redistributed. These systems appear clearly in ancient Mesopotamia, where cuneiform tablets recorded grain inventories and distribution. Though these records were administrative in nature, they indirectly reveal a deep understanding of storage practices. Officials monitored humidity, cleanliness, and pest control within storage areas. In ancient Egypt, large state granaries were closely connected to the Nile's seasonal flooding. Each year, the river deposited fertile sediment across agricultural lands. When waters receded, farmers planted crops that would later be harvested and stored. The resulting grain reserves supported both the population and the state administration. Grain storage also shaped military logistics. Armies moving across large territories needed dependable food supplies. Dried grains could be transported and prepared with relative ease. Soldiers often carried simple grain rations that could be cooked into porridge or flatbread. While grains formed the backbone of preserved food systems, other foods required more active processing. Fruits, for example, contain high moisture and natural sugars. These qualities make them especially vulnerable to fermentation and spoilage. Early preservation methods therefore relied heavily on drying. Sun-dried fruits became common in many agricultural societies. Grapes were dried into raisins. Figs and dates were laid out in the sun until their moisture content fell to stable levels. Apples, apricots, and other fruits could be sliced thin to accelerate drying. In warm climates, drying sometimes took only a few days. In cooler regions, drying might be assisted by ovens or gentle fires. Over time, people learned that thinner slices dried faster and more evenly. They also learned to protect drying foods from insects using cloth coverings or raised platforms. Dried fruit offered several advantages. It retained much of the fruit's original nutrients while becoming lighter and easier to transport. It also provided a concentrated source of energy due to the natural sugars remaining in the fruit. Along trade routes stretching across Asia, North Africa, and Europe, dried fruits became common travel foods. Merchants and travelers valued them for their stability and compactness. In some cases, dried fruit even became a form of trade currency in local markets. Honey also played a quiet role in preservation. Honey has an unusually low water activity and contains natural antimicrobial compounds produced by bees. When foods are submerged in honey, many microorganisms cannot grow easily. Ancient cultures sometimes preserved fruits or nuts in honey to extend their storage life. Archaeologists have discovered jars of honey in ancient Egyptian tombs that remain chemically stable after thousands of years, though the fruit within such jars would eventually change. The honey itself remains one of the most stable natural foods known. Preservation methods for vegetables continued evolving alongside agricultural expansion. Many vegetables are well suited for fermentation, especially when combined with salt. Cabbage became particularly important because of its structure and sugar content. When shredded cabbage is mixed with salt, the salt draws water from the plant cells. This liquid forms a brine, in which naturally occurring lactic acid bacteria begin to grow. These bacteria convert plant sugars into lactic acid. As the acidity increases, harmful microbes are suppressed. Over time, the cabbage becomes sauerkraut, a preserved food with a distinct sour flavor. Similar fermentation techniques developed independently in East Asia, where vegetables were fermented with salt and spices to produce foods such as kimchi. Fermented vegetables often provided essential nutrients during winter months. Vitamin C, which is sensitive to long storage, remains present in fermented vegetables to some extent. Sailors would later rely on fermented foods to help prevent scurvy during long voyages, though the biochemical reasons were not yet understood. In colder northern regions, natural freezing also played a role in preservation. When temperatures fall below freezing, microbial activity slows dramatically. Meat, fish, and plant foods can remain stable for extended periods in frozen environments. Indigenous peoples living in Arctic and subarctic climates made careful use of this natural refrigeration. Fish and meat could be frozen outdoors and stored in snow-covered pits. Some foods were allowed to undergo controlled fermentation within frozen conditions, creating preserved foods adapted to local climates. These techniques required deep familiarity with seasonal patterns. Communities knew when freezing temperatures would arrive and how long they would remain stable. Preservation practices, therefore, followed seasonal cycles closely. In many regions, underground storage became another useful strategy. Beneath the surface of the ground, temperatures tend to remain more stable than above. Root cellars, storage pits, and caves allowed people to keep foods cool, even during warmer seasons. Root vegetables such as carrots, turnips, and potatoes could remain edible for months when stored in cool, dark conditions with moderate humidity. These environments slowed sprouting and microbial growth while preventing excessive drying. Caves were especially valuable in mountainous areas. Natural cave chambers often maintained temperatures near the average annual temperature of the region. In some cultures, caves became dedicated storage sites for cheese, grains, or fermented foods. Over time, these storage practices became increasingly refined. Farmers learned that bruised or damaged produce spoiled more quickly than intact specimens. As a result, careful handling during harvest became part of preservation strategy. Sorting also became common. Foods intended for long storage were selected carefully. Slightly damaged items might be eaten sooner, while the best specimens were reserved for storage. These quiet improvements may seem small, but over generations they significantly reduced food waste. The result was a more stable food supply for entire communities. Preservation also shaped culinary traditions. Many dishes that are now considered traditional foods originally developed as ways to use preserved ingredients. Salted fish soups, fermented vegetable stews, dried meat broths, and grain porridges all reflect the presence of preserved foods. In medieval Europe, for example, salted cod became a staple food. Cod fisheries in the North Atlantic produced large quantities of fish that were cleaned, salted, and dried before being shipped across long distances. This preserved fish could travel from northern waters to inland markets hundreds of kilometers away. The cod itself became firm and dense through drying. When prepared for cooking, it was soaked in water to remove excess salt and restore some moisture. After soaking, it could be used in soups, stews, or baked dishes. Similar preservation industries existed elsewhere. In Scandinavia, fish were dried outdoors in cold winds to produce stockfish. In Japan, fish were salted, dried, and fermented to create stable food supplies. Salted meat also became widely used across Europe and Asia. Pork, in particular, responded well to salting and curing. Hams and bacon were produced through combinations of salting, drying, and sometimes smoking. These cured meats could remain edible for long periods when stored in cool environments. In rural households, meat preservation often took place after seasonal slaughter events. Animals were butchered during colder months, when temperatures helped slow spoilage. Families worked methodically through the meat, cutting portions, rubbing them with salt, and hanging them in cool spaces to cure. Smoke from fireplaces sometimes drifted upward into storage areas, adding further preservation through light smoking. Meanwhile, dairy preservation continued developing in pastoral societies. Cheese varieties expanded as communities experimented with different aging conditions, milk sources, and microbial cultures. Some cheeses were designed for long storage and travel. Hard cheeses with low moisture content could remain stable for months or even years. These foods provided concentrated nutrition in a compact form, which proved valuable for travelers and soldiers. Butter also developed preservation methods. In some cultures, butter was salted heavily before storage. In others, it was clarified through heating to remove water and milk solids, creating forms similar to ghee. These products resisted spoilage more effectively than fresh butter. By the late medieval period, preservation knowledge had spread widely through trade and cultural exchange. Merchants carried preserved foods across seas and deserts. Recipes and techniques traveled alongside goods. However, despite this broad knowledge, preservation still depended heavily on environmental conditions. Warm climates posed constant challenges. Salt was valuable but sometimes expensive. Fermentation required careful control to avoid unwanted microbial growth. Food spoilage, therefore, remained a persistent concern. Entire stores of food could sometimes be lost to mold, pests, or unexpected weather. Because of this uncertainty, societies often preserved food in multiple ways simultaneously. Grains were dried and stored in sealed containers. Meat was salted and smoked. Vegetables were fermented. Fruits were dried or preserved in honey. Each method added a layer of protection against time and decay. In many households, preservation was a central seasonal activity. Summer harvests brought drying racks filled with fruit and herbs. Autumn brought fermentation barrels filled with cabbage and root vegetables. Winter brought meat curing and cold storage. These patterns repeated year after year, quietly sustaining communities. Most people who practiced these techniques did not think of themselves as scientists. Yet their work reflected a practical understanding of chemistry, microbiology, and environmental control. Generations observed what worked and what failed. They adjusted salt levels, drying times, storage conditions, and fermentation vessels. Over centuries, this slow accumulation of knowledge produced a wide range of preservation traditions. The world was gradually becoming more connected through trade and exploration. As goods moved between continents, preservation methods traveled with them. New ingredients appeared in distant kitchens. Old techniques were applied to unfamiliar foods. These exchanges would eventually shape the development of new preservation technologies. But for many centuries, the fundamental methods remained grounded in natural forces. Air, salt, temperature, and microorganisms continued to guide the preservation of food. Human skill lay in learning how to guide these forces gently, without fully understanding the invisible biological processes behind them. In the quiet centuries ahead, curiosity about those hidden processes would begin to grow. Scholars would start asking why certain foods lasted longer than others. They would examine fermentation, decay, and preservation with increasing attention. The answers would arrive slowly, and with them would come new methods that would change the scale and reliability of food preservation across the world. As the medieval period moved slowly toward the early modern era, preservation remained an essential part of everyday life. Most households expected to prepare food for the future. Fresh food was valued, but it was rarely available at all times. Preservation bridged the long spaces between harvests, hunts, and fishing seasons. Many towns maintained public markets where preserved foods appeared beside fresh goods. Barrels of salted fish stood near baskets of dried fruit. Wheels of aged cheese rested on wooden shelves. Jars of fermented vegetables waited in shaded stalls. These foods had traveled from farms, rivers, forests, and coastal waters. Merchants and traders depended on preservation to move goods across long distances. A journey by sea or land might take weeks or months. Without preservation, most food would spoil long before reaching its destination. Salted meat and dried grain formed the basic provisions for many travelers. These foods could survive changing weather and irregular storage conditions. When prepared with care, they remained usable long enough to support trade and exploration. Ships in particular required large stores of preserved food. Sailors working on long voyages could not rely on fresh supplies once they left port. The storage rooms of ships were therefore filled with durable provisions. Hard biscuits made from flour and water became common on many vessels. These biscuits were baked until nearly all moisture had been removed. The result was a very dry, dense food sometimes known as hardtack. Hardtack could last for long periods when kept dry. It was not especially pleasant to eat on its own. Sailors often softened it with water or broth before eating. Despite its simplicity, it provided reliable energy for long journeys. Salted meat also formed a large part of naval rations. Pork and beef were packed into barrels with heavy layers of salt. Over time, the salt drew moisture from the meat and created an environment difficult for many microorganisms. Before cooking, sailors often soaked the salted meat in water to remove some of the salt. The soaking process restored moisture and made the meat more suitable for boiling or stewing. Dried legumes such as peas and beans were also common ship provisions. These foods had naturally low moisture content when dried and could remain stable for extended periods. When cooked in water, they softened and provided protein and nutrients. Despite these preservation efforts, food on long voyages sometimes deteriorated. Salted meat could become excessively hard. Biscuits could attract insects. Stored food might absorb moisture from sea air. Because of this, sailors often faced nutritional deficiencies during long journeys. One well-known example was scurvy, a disease caused by a lack of vitamin C. Symptoms included weakness, bleeding gums, and slow wound healing. Fresh fruits and vegetables contain vitamin C, but these foods spoil quickly. For many years, sailors did not fully understand the connection between diet and scurvy. Over time, however, experience showed that certain preserved foods helped reduce its occurrence. Fermented vegetables, such as sauerkraut, sometimes retained enough vitamin C to provide protection. In the 18th century, naval physicians began recommending citrus fruits and fermented foods during voyages when possible. These developments were gradual. Knowledge spread through observation and repeated experience rather than formal experiments at first. Eventually, the British Navy adopted citrus juice as part of regular rations, significantly reducing cases of scurvy among sailors. While seafaring nations were refining preservation for long voyages, farming communities continued improving local storage practices. One important development involved controlled curing of meats. Curing refers to the use of salt, sometimes combined with other ingredients such as sugar, nitrate salts, and spices, to preserve meat. These compounds influence microbial growth and chemical changes in the meat. In traditional curing methods, meat was rubbed with salt mixtures and stored in cool spaces. Over time, the salt penetrated the tissues, drawing out moisture and slowing bacterial activity. Smoke was sometimes added to enhance preservation. Certain salts known as nitrates and nitrites later became important curing agents. These compounds help prevent the growth of dangerous bacteria, such as Clostridium botulinum. They also influence the color and flavor of cured meats. Historically, nitrates occurred naturally in some salt deposits. People using these salts may have noticed improved preservation without fully understanding why. Over time, curing practices became more standardized. Hams, sausages, and other cured meats became central foods in many European regions. These foods could be stored through winter and used gradually over many months. The curing process also produced distinctive flavors that became part of regional cuisines. Fermented sausages provide an interesting example of combined preservation methods. Ground meat is mixed with salt, and sometimes starter cultures of beneficial bacteria. These bacteria produce lactic acid during fermentation. The resulting acidity helps suppress harmful microorganisms. Meanwhile, drying reduces moisture content. Together, these processes stabilize the sausage and allow safe storage under proper conditions. Elsewhere in the world, similar ideas appeared in different forms. In parts of East and Southeast Asia, fish sauces and fermented seafood products became widely used. Fish were mixed with salt and allowed to ferment slowly in containers. During fermentation, enzymes and bacteria broke down proteins into smaller molecules. The resulting liquids contained amino acids that contributed deep, savory flavors. These sauces were not only seasonings, but also preservation products. Soy fermentation also became highly developed in East Asia. Soybeans were fermented into products such as miso, soy sauce, and fermented bean pastes. These foods involved carefully managed microbial communities. Molds, yeasts, and bacteria worked together to transform the beans into stable foods with long shelf lives. Salt levels, temperature, and fermentation time were all carefully controlled through tradition and observation. These fermentation systems were complex, yet they evolved without modern microbiology. Knowledge passed through apprenticeship and careful practice. Skilled producers learned to recognize subtle signs of successful fermentation. Aroma, color, and texture all served as indicators of progress. Over generations, these observations formed reliable guidelines for producing safe, preserved foods. Sugar preservation also began playing a larger role as sugar production expanded. Sugar acts in a way somewhat similar to salt. High concentrations reduce water activity and create environments where many microorganisms cannot grow easily. When fruits are cooked with large amounts of sugar, the resulting mixtures can become stable for long periods. Jams, jellies, and fruit preserves developed through this principle. Boiling the fruit mixture also helped destroy many microbes present in the fruit. In early stages, sugar was expensive and sometimes reserved for wealthy households. As sugar cultivation expanded in tropical regions, its availability increased in Europe and other parts of the world. Preserved fruits became more common. Candied fruits were another example. Fruits were gradually soaked in sugar syrups of increasing concentration. Over time, the sugar replaced much of the fruit's water content. This process created sweet preserved foods that could be stored for long periods. By the 17th century, preservation knowledge had accumulated across many cultures. Yet a fundamental mystery remained. People knew how to preserve food, but they did not yet know precisely why these methods worked. The idea of microorganisms causing spoilage had not yet been fully developed. Many scholars believed in spontaneous generation, the concept that life could arise naturally from non-living material. According to this belief, insects or tiny creatures might appear in food simply because conditions allowed them to form. Without microscopes capable of detailed observation, the true causes of spoilage remained hidden. Nevertheless, curiosity about food preservation began to attract scientific interest. Early investigators studied fermentation, decay, and storage with increasing attention. In the 17th century, improvements in microscopy began revealing a previously invisible world. Scientists such as Antony van Leeuwenhoek observed tiny living organisms in water and other materials. These organisms would later be recognized as bacteria and other microbes. At first, the connection between these microorganisms and food spoilage was not fully understood. Observations accumulated slowly. Some scientists suspected that these tiny forms of life might play roles in fermentation and decay. Meanwhile, preservation challenges continued to influence daily life. Urban populations were growing. Cities required large and reliable food supplies. Traditional preservation methods remained valuable, but sometimes limited in scale. Governments and institutions began encouraging innovation in food storage and transport. The need for better preservation became especially clear during military campaigns. Armies moving across continents required food that could last for long periods without spoiling. Salted meat and dried grain remained the primary solutions, but they were not always sufficient. During the late 18th century, a new challenge emerged that would eventually lead to one of the most important preservation innovations. The French government offered a prize for anyone who could develop a reliable method for preserving large quantities of food for military use. The search for this solution would eventually lead to the development of a new method based on heat and sealed containers. This method would mark the beginning of modern food preservation. But before that moment arrived, the world still relied mostly on the ancient partnership between humans and natural processes: drying, salting, smoking, fermentation, sugar preservation, cold storage. These methods had carried civilizations for thousands of years. They allowed communities to stretch abundance across time. They reduced waste. They supported trade, travel, and cultural exchange. Slowly, quietly, knowledge continued to deepen. The invisible life within food would soon become clearer. And with that understanding, preservation methods would begin to change in ways earlier generations could not have imagined. Near the end of the 18th century, the need for reliable food preservation became more pressing in parts of Europe. Armies were moving across long distances. Navies were sailing for months at a time. Governments understood that soldiers and sailors required food that could remain safe for extended periods. Traditional preserved foods were useful, but they had limits. Salted meat could become excessively hard or unpleasant after long storage. Dried foods sometimes lost flavor and texture. Fermented foods worked well in certain cases, yet they did not suit every ingredient. In 1795, the French government announced a prize. The goal was simple in description, though difficult in practice. Officials wanted a method that could preserve large quantities of food for military use. The preserved food needed to remain safe and edible during transport and storage. Many people attempted to solve the problem. Among them was a French confectioner named Nicolas Appert. Appert had experience working with fruits, sugar, and cooking processes. He began experimenting with ways to protect food from spoilage. Appert did not know about microorganisms. The science of microbiology had not yet been fully developed. Instead, he relied on careful observation. He noticed that foods cooked and sealed in containers sometimes lasted longer than foods left exposed to air. Over many years, he refined a method. Food was placed into glass bottles. The bottles were sealed with cork and sometimes wax. After sealing, the bottles were heated in boiling water for a period of time. This process produced a remarkable effect. Foods treated in this way could remain edible for months, sometimes even longer. Fruits, vegetables, soups, and meats all showed improved stability. Appert eventually published his method in 1810. The process became known as appertization. Though the scientific explanation was not yet clear, the method had demonstrated that heat and sealed containers could work together to prevent spoilage. The heating step destroyed many microorganisms present in the food. The sealed container prevented new microbes from entering. Without these organisms, the food remained stable for much longer than usual. Glass bottles worked well, but they were fragile. For military and naval use, stronger containers were needed. Around the same time, metal containers began to appear. In England, inventors developed tin, plated iron cans that could be sealed after filling. These early cans were thick and heavy compared to modern versions. Opening them often required tools such as hammers or chisels. Despite their weight, cans offered advantages. They were less fragile than glass and easier to transport in large quantities. Foods preserved in sealed metal cans could survive long journeys by sea or land. The early canning process followed similar principles to Appert's work. Food was placed inside the container. The container was sealed. Then it was heated in boiling water or steam for a specific period of time. The heat destroyed many microorganisms. The sealed environment prevented contamination from outside sources. Together, these steps created a stable, preserved food. At first, canning remained a slow and somewhat experimental process. Heating times were not yet well understood. Some foods required longer heating to destroy harmful organisms. Others could be damaged by excessive heat. Occasionally, canned foods spoiled despite the process. In rare cases, dangerous bacteria could survive if heating was insufficient. The most serious concern involved a bacterium now known as Clostridium botulinum. This organism produces a powerful toxin under certain conditions. It thrives in low oxygen environments such as sealed containers when heat treatment is not adequate. At the time, however, scientists did not yet know about this organism. Despite these challenges, canning continued improving. By the mid-19th century, it had become an important method of food preservation. Military forces, ships, and remote settlements all benefited from foods that could remain safe for long periods. Factories began producing canned vegetables, fruits, soups, and meats. Industrial production gradually replaced small-scale experiments. Machinery helped seal cans more efficiently. Heating processes became more consistent. During this same period, scientific understanding of food spoilage began to advance. Researchers were slowly uncovering the role of microorganisms in fermentation and decay. One of the most influential figures in this work was Louis Pasteur. In the mid-19th century, Pasteur conducted experiments that showed microorganisms were responsible for fermentation processes. He demonstrated that when liquids were heated and protected from contamination, they remained stable. When exposed to airborne microbes, fermentation and spoilage occurred. Pasteur's work challenged the long-standing belief in spontaneous generation. Instead, it showed that microorganisms came from existing life forms and could be controlled through heat and sanitation. These discoveries helped explain why heating sealed containers preserved food. Heat destroyed microorganisms already present. Sealing prevented new microbes from entering. Pasteur also developed a related preservation method now known as pasteurization. In this process, liquids such as milk or wine are heated to moderate temperatures for short periods. The heat reduces microbial populations without severely altering flavor or quality. Pasteurization does not sterilize food completely. Instead, it lowers the number of microbes to safer levels and slows spoilage. When combined with refrigeration or sealed containers, pasteurized foods can remain stable for longer periods. Milk became one of the most important products to benefit from pasteurization. Fresh milk spoils quickly because it contains nutrients that support microbial growth. Pasteurization greatly improved its safety and shelf life. As the 19th century continued, preservation methods became increasingly scientific. Researchers studied heat transfer, microbial resistance, and chemical reactions in food. Their work helped refine both canning and pasteurization. Meanwhile, another preservation approach was beginning to emerge through advances in mechanical technology. This method involved the control of temperature through artificial cooling. For most of human history, cold storage depended on natural conditions. Winter ice, Underground cellars and mountain caves provided cool environments. These methods worked well in certain climates, but were limited in warmer regions. In the early 19th century, inventors began experimenting with mechanical refrigeration. These systems used chemical processes to absorb heat and produce cooling. The earliest machines were large and complex. They were mainly used in breweries and food processing facilities. Over time, however, refrigeration technology became more reliable. Artificial cooling opened new possibilities for food preservation. Lower temperatures slow the growth of microorganisms and reduce chemical reactions in food. Even a small decrease in temperature can extend the shelf life of many products. Ice also continued playing an important role. During the 19th century, natural ice was harvested from frozen lakes and rivers in colder regions. Large blocks of ice were cut and stored in insulated ice houses. These ice blocks could then be transported to cities or warmer climates. Ice storage allowed perishable foods such as meat, fish, and dairy products to remain fresh for longer periods during transport and sale. In some cities, ice delivery became a regular service. Households stored food in insulated boxes filled with ice. These early ice boxes functioned as simple refrigerators before electric systems became common. Together, these developments slowly changed the way societies handled food. Canning provided long-term storage for cooked foods. Pasteurization improved the safety of liquids such as milk. Ice and refrigeration slowed spoilage for fresh products. Yet the transition was gradual. Traditional preservation methods did not disappear. Drying, fermentation, salting, and smoking continued alongside newer technologies. Many foods were still preserved in the ways people had practiced for centuries. In rural areas especially, seasonal preservation remained an important part of household life. But the foundations of modern food preservation had begun to form. Heat treatment, sealed containers, and controlled temperature would shape the future of food storage. Scientists were now beginning to understand the invisible organisms that had always influenced the fate of food. With this knowledge came the ability to design preservation methods with greater precision. The quiet partnership between observation and science continued to deepen. And as the 19th century moved forward, preservation would become increasingly connected to industry, chemistry, and global food systems. During the late 19th century, food preservation gradually entered a more scientific phase. Earlier methods had developed through long experience. Now researchers began to measure, test, and describe the processes involved. Microscopes had revealed the presence of bacteria, yeasts, and molds. Scientists slowly learned how these organisms behaved under different conditions. Temperature, moisture, acidity, and oxygen all influenced microbial growth. These insights helped explain many traditional preservation methods. Drying removed water that microbes needed. Salt and sugar reduced available moisture through osmotic pressure. Fermentation allowed beneficial microbes to produce acids that suppressed harmful ones. Heat treatment became easier to understand as well. When food was heated to sufficient temperatures for enough time, most microorganisms were destroyed. If the food was then sealed from contamination, spoilage could be delayed for long periods. Researchers began studying the temperatures required to inactivate specific microbes. Some organisms were relatively easy to destroy. Others formed resistant spores that could survive brief heating. Understanding these differences helped refine canning processes. Heating times were adjusted according to the type of food and the size of the container. Low, acid foods such as meats required more careful treatment than acidic foods like fruits. Gradually, canning became more reliable. Industrial canneries expanded in many countries. Factories processed vegetables, fish, soups, and meats in large batches. Machines sealed cans more quickly than hand methods. Railways and steamships allowed preserved foods to travel further than before. Canned goods reached distant regions that previously relied on local harvests. Urban populations benefited from foods produced far from the cities where they were consumed. During this period, the can itself also improved. Early cans were heavy and required solder-containing lead. Over time, manufacturers developed better sealing techniques and thinner metal sheets. New designs made cans easier to open and safer to use. Glass jars also remained important for home preservation. In the United States, John Landis Mason introduced a screw-top glass jar with a rubber sealing ring in 1858. This design allowed households to preserve fruits and vegetables using boiling water baths. The Mason jar became widely used for home canning. Families preserved seasonal produce during harvest months. Fruits were cooked with sugar and sealed in jars. Vegetables were heated and stored for winter use. Home preservation remained common well into the 20th century. Many households relied on their own preserved foods as part of everyday cooking. While canning was spreading, refrigeration technology continued developing. Mechanical refrigeration systems improved in reliability and efficiency during the late 19th century. At first, these systems were used mainly in industrial settings. Breweries, meat packing plants, and cold storage warehouses began installing refrigeration machines. These machines circulated refrigerant chemicals through pipes and coils to absorb heat. Cold storage warehouses allowed large quantities of food to be kept at low temperatures. Meat, butter, eggs, and fruit could remain fresh longer when stored in chilled environments. Refrigerated railway cars soon followed. These cars used ice or mechanical cooling to maintain low temperatures during transport. Fresh meat from slaughterhouses could now reach cities hundreds or even thousands of kilometers away. This development changed food distribution in many countries. Instead of relying only on local farms, cities could receive fresh products from distant agricultural regions. The meat packing industry in the United States offers a clear example. Large slaughterhouses processed cattle and pigs in central locations. Refrigerated rail cars carried the chilled meat to urban markets across the country. The result was a new food network based on temperature control rather than solely on preservation through salt or drying. Natural ice still played a large role during this period. Ice harvesting remained a major seasonal activity in colder regions. Workers cut large blocks from frozen lakes and stored them in insulated buildings. These ice blocks were transported to cities by rail or ship. Ice deliveries allowed businesses and households to keep foods cool during warmer months. Iceboxes became common household items. These cabinets were insulated and designed to hold a block of ice in an upper compartment. Cold air circulated downward to keep food chilled. Although iceboxes required regular ice deliveries, they represented a significant improvement over earlier storage methods. Milk, butter, and fresh meats could remain usable longer than before. Meanwhile, scientists continued studying the effects of temperature on food spoilage. They observed that microbial growth slowed dramatically as temperatures decreased. At temperatures near freezing, many bacteria grow very slowly. Chemical reactions within food also slow down. These effects combine to extend shelf life. Refrigeration, therefore, became a preservation method in its own right. Unlike drying or salting, it does not remove water or alter flavor significantly. Instead, it delays the processes that lead to spoilage. Another important development appeared near the end of the 19th century. This method involved rapid freezing. Slow freezing had always been possible in cold climates. However, slow freezing can damage food tissues. Large ice crystals form within cells and break cell walls. When the food thaws, texture can become soft or watery. Researchers discovered that faster freezing produced smaller ice crystals. Smaller crystals caused less damage to the structure of the food. Although large-scale frozen food production would not appear until the 20th century, these early observations laid the groundwork for later innovation. Chemical preservatives also began attracting attention during this time. Certain compounds could slow microbial growth when added to food in small amounts. Substances such as sulfur dioxide were used to preserve dried fruits and wines. Benzoates and salicylates were sometimes used in beverages and sauces. However, the safety of chemical preservatives soon became a subject of debate. Some compounds were later restricted or replaced as food safety science advanced. Governments began introducing food safety regulations in response to growing industrial food production. In the United States, the Pure Food and Drug Act of 1906 established standards for labeling and prohibited certain adulterated foods. Similar laws appeared in other countries. These regulations aimed to protect consumers and ensure that preserved foods were produced safely. By the early 20th century, several major preservation technologies existed side by side. Traditional methods such as drying, salting, and fermentation remained widely practiced. At the same time, industrial canning and refrigeration were expanding rapidly. Each method served a different purpose. Drying created lightweight foods suitable for long storage and transport. Fermentation produced stable foods with distinctive flavors. Canning allowed cooked meals to be stored for months or years. Refrigeration preserved fresh foods for shorter periods while maintaining their original qualities. Together, these methods formed the foundation of modern food preservation. Yet one more important innovation would soon reshape the relationship between time and food. That innovation would come from improvements in freezing technology. It would allow foods to be preserved while remaining remarkably close to their fresh state. But the development of frozen food would require careful study of temperature, packaging, and food chemistry. And those developments would unfold slowly during the early decades of the 20th century. As the 20th century began, refrigeration and canning were already established methods of preserving food. Both were effective, yet each had limits. Canning involved cooking the food during processing. This extended shelf life, but it also changed texture and flavor. Refrigeration slowed spoilage, but could not preserve food indefinitely. Researchers continued looking for methods that would keep food closer to its fresh state. One approach focused on freezing. Freezing had always been part of life in cold climates. In northern regions, fish and meat could freeze naturally during winter. These foods remained edible for long periods while temperatures stayed low. However, natural freezing often occurred slowly. When food freezes slowly, large ice crystals form inside its cells. These crystals can damage cell walls. After thawing, the food may lose some firmness and release extra moisture. In the early 20th century, scientists began studying how freezing speed affected food quality. They learned that rapid freezing produced much smaller ice crystals. Smaller crystals caused less structural damage. One of the most influential figures in this development was Clarence Birdseye. In the 1920s, Birdseye observed traditional fishing practices in northern Canada. Fishermen sometimes froze freshly caught fish in very cold outdoor air. The fish froze quickly under those conditions. When thawed later, the texture remained closer to fresh fish than fish frozen slowly in ordinary ice storage. Birdseye began experimenting with mechanical systems that could freeze foods rapidly. His equipment pressed packaged food between cold metal plates. The plates removed heat quickly, allowing the food to freeze in a short time. This method became known as quick freezing. It produced frozen foods with improved texture and flavor after thawing. Vegetables, fish, and meats all benefited from faster freezing methods. By the late 1920s, commercial frozen food production had begun. Early frozen products included vegetables such as peas and spinach. These foods were blanched briefly before freezing. Blanching involves heating vegetables in hot water or steam for a short time. This step stops certain enzymes that would otherwise cause flavor and color changes during storage. After blanching, the vegetables were cooled and frozen quickly. Proper packaging helped protect the frozen food from air and moisture loss. Frozen foods required a continuous cold chain. This meant that food had to remain frozen during storage, transport, and retail display. Maintaining these low temperatures required reliable refrigeration systems. As electrical refrigeration improved during the early 20th century, frozen food distribution became more practical. Supermarkets began installing freezer cabinets. Households gradually adopted electric refrigerators and freezers. These appliances allowed consumers to store frozen foods safely at home. Over time, frozen food became a normal part of everyday life in many countries. Freezing offered several advantages. It slowed microbial growth almost completely at sufficiently low temperatures. It also slowed chemical reactions that cause spoilage. Unlike canning, freezing did not require cooking the food completely during preservation. Many foods therefore retained textures and flavors closer to their original state. At the same time, refrigeration itself continued improving. Electric refrigerators replaced many earlier iceboxes. These appliances used compressors and refrigerants to circulate cold air inside insulated cabinets. By the mid-20th century, refrigerators had become common household equipment in many parts of the world. Fresh milk, vegetables, and meats could now be stored safely for several days or longer. Refrigeration changed everyday cooking habits. People no longer needed to purchase food daily from local markets. Perishable items could remain fresh at home between shopping trips. Alongside freezing and refrigeration, scientists explored additional preservation techniques. One method involved removing air from food packaging. Oxygen supports many chemical reactions that lead to spoilage. It also allows certain microorganisms to grow. By reducing oxygen inside a package, these processes can be slowed. Vacuum packaging removes most of the air surrounding a food product. The food is sealed inside a plastic or laminated material after air has been withdrawn. This method helps reduce oxidation and microbial growth. Vacuum packaging became widely used for meats, cheeses, and prepared foods. Combined with refrigeration, it significantly extends shelf life. Another related approach is modified atmosphere packaging. Instead of simply removing air, the air inside the package is replaced with a mixture of gases. Carbon dioxide, nitrogen, and sometimes small amounts of oxygen are used in carefully controlled proportions. These gases influence microbial growth and chemical reactions inside the package. For example, carbon dioxide can slow the growth of many spoilage bacteria. Nitrogen is often used as an inert filler gas that does not react with food. Modified atmosphere packaging is commonly used for fresh meats, salads, baked goods, and snack foods. It allows products to remain fresh longer while still appearing close to their natural state. During the mid-20th century, another preservation method also received attention. This method involved ionizing radiation. Food irradiation exposes food to controlled doses of radiation. This radiation damages the DNA of microorganisms and insects present in the food. When microbes cannot reproduce, spoilage, and foodborne illness are reduced. Irradiation can also slow the ripening of certain fruits and vegetables. The process does not make food radioactive. Instead, it transfers energy that disrupts biological structures within microorganisms. Irradiation has been used for products such as spices, dried herbs, and certain fruits. In some cases, it helps eliminate insects or pathogens without raising the temperature of the food significantly. Despite its effectiveness, irradiation has sometimes faced public hesitation. Concerns about radiation have influenced how widely the method is adopted in different countries. Throughout these developments, traditional preservation methods remained important as well. Fermented foods continued to be produced around the world. Drying remained essential in many climates. Even in modern industrial systems, these older techniques still play valuable roles. Dried grains, fermented dairy products, cured meats, and pickled vegetables remain widely consumed. By the late 20th century, food preservation had become a combination of science, engineering, and long cultural tradition. Canning factories operated with carefully measured heating processes. Refrigerated transport moved fresh products across continents. Freezing preserved vegetables and meats for long storage. At the same time, ancient practices continued quietly in kitchens, farms, and small workshops. The fundamental goal remained the same as it had been thousands of years earlier: to slow the natural changes that occur in food, to protect it from microorganisms, enzymes, and chemical reactions, and to extend the time between harvest and consumption. As scientific understanding deepened, preservation methods became more precise. Yet the principles guiding them remained closely connected to the same natural forces that early humans had once observed beside fires, rivers, and drying racks. During the later decades of the 20th century, food preservation continued to evolve quietly. Many of the major techniques were already in place. Canning, refrigeration, freezing, drying, fermentation, and curing all remained important. What changed was the precision with which these methods were applied. Scientists learned more about the small biological and chemical processes inside food. Microbiology, chemistry, and engineering gradually became closely connected to food production. Researchers measured how quickly different microorganisms grow at different temperatures. They studied how salt levels, acidity, and oxygen influence microbial survival. These measurements helped refine preservation techniques. For example, heating processes in canning became carefully calculated. Scientists determined the exact time and temperature required to destroy specific microorganisms. The goal was to make food safe while preserving as much quality as possible. Low-acid foods, such as meats and many vegetables, require higher temperatures during canning. These temperatures are often achieved using pressurized steam systems known as pressure canners or retorts. The pressure allows water to reach temperatures above normal boiling. Acidic foods, such as many fruits and tomatoes, require less intense heating. Their natural acidity already inhibits the growth of certain dangerous bacteria. Understanding these differences allowed producers to design safe preservation processes for many types of food. At the same time, refrigeration systems continued improving. New refrigerant chemicals replaced earlier substances that were sometimes toxic or environmentally harmful. Compressors became more efficient. Insulation materials improved. Cold storage warehouses expanded in size and number. Fresh fruits from one continent could now travel across oceans in refrigerated ships. Vegetables harvested in one region could appear in markets far away. Temperature monitoring also became more precise. Thermometers, sensors, and automated systems allowed producers to maintain stable temperatures during storage and transport. These systems formed what is now called the cold chain. The cold chain refers to the continuous control of low temperatures from the moment food is harvested or processed until it reaches the consumer. If the cold chain is interrupted, microorganisms can begin growing again. For this reason, maintaining stable refrigeration is essential for many modern food systems. Freezing technology also advanced. Large industrial freezers were designed to freeze food rapidly and evenly. Methods such as blast freezing used very cold air, moving at high speed across food surfaces. Another method, known as individual quick freezing, allowed small food items to freeze separately rather than clumping together. This technique works well for foods such as peas, berries, and shrimp. Frozen foods became widely available in supermarkets during the mid and late 20th century. Packaging materials also improved during this time. Plastics and laminated films help protect foods from moisture and oxygen. Proper packaging plays an important role in preservation. Even frozen foods can slowly change over time if exposed to air. One example is freezer burn, which occurs when moisture evaporates from the surface of frozen food. Modern packaging reduces these effects by creating barriers against air and moisture loss. Scientists also studied enzymes present in food. Enzymes are natural proteins that continue working after harvest or slaughter. They can cause changes in color, flavor, and texture. For example, certain enzymes cause fruits, such as apples, to turn brown when cut. Other enzymes slowly alter the flavor of stored vegetables. Blanching, which briefly heats vegetables before freezing, was found to deactivate many of these enzymes. This simple step helps maintain color and flavor during frozen storage. Another preservation approach that developed further during the 20th century involved dehydration through controlled drying. Industrial drying equipment allowed food to be dried under carefully controlled temperatures and airflow. Removing water greatly reduces microbial growth and chemical reactions. Some drying methods use heated air to remove moisture. Others rely on freeze drying. Freeze drying is a more complex process. In freeze drying, food is first frozen. Then the surrounding pressure is lowered. Under these conditions, ice inside the food can change directly into water vapor through a process known as sublimation. Because the water leaves without passing through a liquid stage, the structure of the food remains largely intact. Freeze-dried foods are extremely light and dry. When water is added again, many freeze-dried foods return close to their original shape and texture. This technique became important for products such as instant coffee, dried fruits, and foods used in space travel. Space missions required foods that were lightweight and stable for long periods. Freeze-drying provided an effective solution. During the late 20th century, food safety systems also became more organized. One widely used approach is known as HACCP, which stands for Hazard Analysis and Critical Control Points. This system identifies points during food production where contamination could occur. Each point is monitored and controlled to reduce risk. For example, heating temperatures during canning are monitored carefully. Refrigeration temperatures are recorded during storage and transport. Clean handling procedures are used during packaging. HACCP systems are now common in food industries around the world. They help ensure that preserved foods remain safe for consumers. At the same time, interest in traditional preservation methods continued. Fermented foods such as yogurt, kimchi, sauerkraut, miso, and sourdough bread remained important parts of many diets. Scientists studying these foods discovered complex microbial communities living within them. These communities include beneficial bacteria and yeasts that contribute to flavor and preservation. Research into these microorganisms expanded during the late 20th century. Some studies explored how fermented foods influence digestion and the human microbiome. Although these discoveries are relatively recent, the foods themselves have been part of human diets for thousands of years. In many parts of the world, households still practice seasonal preservation, much as their ancestors did. Fruits are dried in the sun. Vegetables are pickled in jars. Meats are salted and cured. These traditions often exist alongside modern appliances. A refrigerator may stand beside shelves filled with homemade preserves. The long history of food preservation, therefore, continues in both traditional and technological forms. Across thousands of years, the central challenge has remained steady. Food changes with time. Microorganisms grow. Enzymes continue their work. Chemical reactions slowly alter flavor and texture. Preservation methods do not stop these processes completely. Instead, they slow them. Salt reduces water activity. Cold slows microbial growth. Heat destroys microorganisms. Drying removes moisture. Fermentation reshapes the microbial environment. Each method influences the delicate balance between food and time. As the 21st century approached, preservation technology continued improving quietly. Scientists explored new packaging materials. Sensors became smaller and more accurate. Storage systems became more efficient. Yet even with all these advances, the fundamental ideas remained closely connected to observations made long ago. Food lasts longer when water, temperature, oxygen, and microorganisms are carefully controlled. This understanding, developed slowly over many generations, continues guiding how food is preserved today. As the 21st century continues, food preservation remains a quiet but constant part of everyday life. Most people encounter it many times each day, often without noticing. A carton of milk in the refrigerator, frozen vegetables in a freezer drawer, bread sealed in a plastic bag, a jar of pickled cucumbers resting on a shelf. Each of these foods reflects a long history of observation, experimentation, and careful adjustment. Modern preservation systems combine many ideas developed across thousands of years. Some methods rely on ancient principles. Others depend on modern engineering. Together they form a network that supports the global movement of food. One important area of development has been packaging technology. Packaging does more than hold food. It protects food from oxygen, moisture, light, and microorganisms. Many modern packages are made from several layers of materials. Plastics, aluminum films, and paper may be combined in thin sheets. Each layer performs a different task. Some layers block oxygen. Others block moisture. Some provide strength so the package can withstand transport. Vacuum packaging, which removes air from around the food, continues to be widely used. Removing oxygen slows the growth of many spoilage organisms and reduces oxidation reactions. Another method, called modified atmosphere packaging, adjusts the mixture of gases inside the package. Carbon dioxide, nitrogen, and controlled levels of oxygen are used to create stable conditions. For example, fresh salad greens are often packaged in bags filled with a specific gas mixture. This mixture slows respiration in the plant tissues and reduces microbial growth. The result is a longer shelf life while the food still appears fresh. Temperature control also remains essential. Refrigeration and freezing systems are now part of a global cold chain that moves food across large distances. Fruits harvested in South America may travel by refrigerated ship to markets in Europe. Fish caught in the Pacific Ocean may be frozen on board vessels before being transported to distant ports. Sensors and digital monitoring systems track temperatures during transport. If temperatures rise above safe levels, alerts can be issued so the problem can be corrected. These systems help maintain consistent preservation conditions even when food travels thousands of kilometers. Scientists also continue studying the biology of microorganisms in food. Modern genetic tools allow researchers to identify bacteria and fungi with great precision. This knowledge helps producers understand which organisms cause spoilage and which contribute beneficial effects in fermentation. Starter cultures are now widely used in many fermented foods. These cultures contain selected strains of bacteria or yeast that produce consistent results. Yogurt, cheese, sourdough bread, and fermented vegetables are often produced using carefully maintained microbial cultures. These cultures help guide fermentation while limiting unwanted microbes. At the same time, many traditional fermentation practices still rely on natural microbial communities present on the ingredients themselves. Both approaches reflect the same underlying principle. Microorganisms shape the transformation and preservation of food. Another area of study involves high-pressure processing. This method uses extremely high pressure to inactivate microorganisms in food. Food sealed in flexible packaging is placed in a chamber filled with water. The pressure inside the chamber is increased to very high levels, sometimes several thousand times greater than atmospheric pressure. Under these conditions, many microorganisms are damaged or destroyed. Because the process does not rely on high heat, the flavor and texture of the food can remain closer to its fresh state. High-pressure processing is used for certain fruit juices, ready-to-eat meats, and some packaged meals. Researchers are also studying pulsed electric fields and other emerging technologies. These methods use short bursts of energy to disrupt microbial cells. Such techniques are still developing, and their use depends on safety evaluations and practical considerations. Despite these modern innovations, the basic principles guiding food preservation remain familiar. Microorganisms require water, nutrients, and suitable temperatures to grow. When water is reduced through drying, microbial growth slows. When salt or sugar binds available water, microbial activity decreases. When heat is applied for sufficient time, many microbes are destroyed. When temperature is lowered through refrigeration or freezing, microbial growth slows dramatically. When acidity increases during fermentation, many harmful organisms cannot survive. These principles have been present throughout the entire history of food preservation. Long before microscopes revealed bacteria, people noticed that dried meat lasted longer than fresh meat. They observed that salted fish resisted spoilage. They discovered that fermented vegetables remained edible through winter. Over centuries, these observations gradually formed a practical body of knowledge. Later, science provided explanations for the processes involved. Microbiology revealed the organisms responsible for fermentation and decay. Chemistry explained how salt, sugar, and acids influence water activity and microbial survival. Engineering provided machines capable of freezing, heating, and cooling food with precision. Together, these fields shaped the modern systems that store and distribute food across the world. Yet preservation remains closely tied to simple natural processes. Food is part of the living world. Even after harvest or slaughter, biological activity continues within it. Enzymes remain active. Microorganisms continue searching for nutrients. Chemical reactions slowly change flavor, color, and texture. Preservation methods guide these processes rather than stopping them completely. Dry air slows change. Cold temperatures slow change. Salted environments slow change. Sealed containers protect food from contamination. These influences gently shift the balance between stability and decay. Throughout history, preservation has allowed human communities to extend the usefulness of food across time. Harvests that arrive all at once can be stored for months. Fish caught during brief seasons can be eaten later. Milk can be transformed into cheese or yogurt, that lasts far longer than fresh milk. Vegetables gathered in autumn can remain edible through winter. Without preservation, human settlement patterns would have been very different. Cities would have been smaller. Long voyages would have been difficult. Trade between distant regions would have been limited. Preservation made it possible to separate the moment of harvest from the moment of eating. It allowed food to travel. It allowed food to wait. The story of food preservation, therefore, stretches quietly across the entire history of civilization. It begins with sunlight, drying strips of meat beside ancient fires. It continues through clay jars filled with fermented vegetables, through barrels of salted fish carried on wooden ships, through glass bottles heated in boiling water, through steel cans sealed in factories, through refrigerated trains crossing continents, through frozen vegetables stacked in supermarket freezers. Each stage reflects the same careful effort to slow time, not to stop it entirely, only to move a little more slowly. And so, even today, preservation remains a calm partnership between human knowledge and the natural processes that shape every living thing. Food changes with time, but with patience, observation, and care, that time can be gently extended. Thank you for spending this quiet time listening. The long story of food preservation stretches across thousands of years through small observations, careful habits, and patient learning. From drying racks in the sun to modern refrigeration systems, each method reflects a simple effort to help food remain useful a little longer. If you enjoyed this calm journey through history, you may consider subscribing to the channel. More slow and thoughtful stories are always on the way. For now, the day is ending. The mind can rest, just as the world itself moves at a slower pace during the night. Thank you again for listening, and I wish you a peaceful night and gentle sleep.